Hello everyone, my name is Kosi Okiki. Today, I'll be presenting on focal loss, a powerful technique for handling class imbalance in machine learning tasks. This problem affects real-world use cases like fraud detection, rare disease prediction, and much more. Here's a roadmap of the agenda for today. I'll begin with the class imbalance issue, then proceed to walking through how standard loss functions fall short, then introducing focal loss and show how it solves the problem, both in theory and then afterwards in application. And then lastly, there will be the conclusion. Now, we will speak about the challenge to class imbalance. In many real-world datasets, one class vastly outnumbers the other. For example, in fraud detection, only a tiny fraction of cases are genuinely fraudulent. Standard models often ignore that minority class, which in turn hurts precision as well as recall. These models may also favor the majority class, and in turn, minority classes suffer. Why standard loss functions fail, and the weaknesses of cross-entropy. Cross-entropy is a widely used loss function, but it doesn't distinguish between easy and hard examples, meaning it spends just as much energy on obvious predictions as it does on the nuanced edge cases. Therefore, if a model predicts the majority class correctly, it gets rewarded, even if it keeps misclassifying rare events. Here we see the standard formula for cross-entropy loss used in classification tasks. Essentially, what this formula does is it calculates how far off the model's predicted probabilities, which is P sub c, it is from the true labels, which are Y sub c. If Y sub c equals 1, then that means that class C is the true label, and the loss only considers log of P sub c, ignoring other classes. But there is a catch. This loss treats every sample equally. I must reiterate that. It treats every sample equally. So regardless of how easy or how hard it is to classify. This is where focal loss comes in. What it does is it will reweigh the contribution of the easy examples versus the hard examples. So why may there be a need for focused learning? Well, primarily is to prioritize hard examples. Again, rare classes are often underrepresented, and the focus must shift during training to compensate. So essentially what we really want is a way to focus the model's learning effort on the most difficult, rare, and important examples. And that's essentially exactly what focal loss offers. The need for a smarter loss function. So, what if we could reduce the impact of easy examples, while simultaneously letting our model focus more on the hard cases? Well, focal loss was introduced by Facebook AI research for object detection in highly imbalanced scenarios. It literally adds a focus term to shift learning toward the rare and important cases. Introducing focal loss. So, focal loss is an extension of cross entropy. It also adds a focusing parameter called gamma. And what it does is it reduces the loss from the easy examples. So, the key addition here is the 1 minus p sub t to the gamma term. This downweights easy examples when p sub t is close to 1, and upweights harder ones or harder examples when p sub t is close to 0. Visualizing gamma. So, this plot shows how different values of gamma affect the behavior of focal loss itself. As we can see, as gamma increases, the loss curve flattens out much more quickly, meaning that well-classified, easy examples contribute less to the overall loss. Again, higher gamma yields more focus on the harder examples. In contrast, harder misclassified examples are weighted more heavily, and the model focuses on learning from those. So essentially, higher gamma values increase the model's focus on correcting its mistakes, not reinforcing what it already gets right. So here we can analyze how focal loss is affected as we alter different terms in the formula or in the function. So for the easy examples, as the complete term 1 minus p sub t raised to the gamma becomes smaller, less loss is accrued. For harder examples, a low p sub t yields more weight in the loss. Gamma focuses learning where it's needed most. So if the model is confident, say it predicts a p sub t equals 0.95, then this loss is dampened by the complete term 1 minus p sub t to the gamma, effectively saying, hey, we've already got this one. But if the model is unsure, for example, a p sub t of, let's say, 0.3, that example's loss remains high and keeps the model's attention. This makes training much more efficient, especially when dealing with class imbalances. So these are some of the effects of gamma. What this graph shows exactly is how focal loss behaves differently than standard cross entropy. If we choose a gamma of 0, then we are essentially emulating cross entropy. A higher gamma yields shrinkage of the easy example's loss. And for gamma itself, we tend to use a range from 1 to 5. In this graph to the right, you see each curve represents a different gamma value. The blue line is a standard CE, standard cross entropy, again, when gamma is 0. It penalizes all mistakes equally. But when we raise gamma, the penalty for well-classified examples drops. That means the model doesn't waste effort on examples it already gets right. Instead, it focuses on the ones it struggles with, the ones that are highly imbalanced. And that's what makes focal loss powerful in imbalanced settings. Why focal loss works. So, now that we've seen how gamma changes the shape of the loss curve, let's talk more about why focal loss actually works and why it outperforms standard cross entropy in imbalanced settings. With traditional binary cross entropy, every example, whether easy or hard, is treated equally. That's fine when your data set is balanced. But in cases like fraud detection or medical diagnoses, where the rare class is extremely underrepresented, this uniform weighting causes the model to learn from the majority class more than anything else. What focal loss will do is shift the attention toward the tough edge case examples. These are typically the minority class samples, the ones your model would otherwise ignore. So, by down-weighting easier examples and emphasizing the more challenging ones, focal loss creates a more focused and efficient learning signal. This is especially important when catching rare events matters. This is especially important when catching rare events matter more than just maintaining high accuracy, because in imbalanced data sets, accuracy alone can be misleading. So, focal loss isn't just a theoretical improvement, it's actively used in real world systems. One major example is RetinaNet, a highly accurate object detector that relies on focal loss to improve performance on hard to detect objects and images. Beyond computer vision, though, focal loss is gaining traction in high stakes fields like finance and healthcare, where detecting rare events like fraud or early signs of disease is very, very critical. In these contexts, traditional loss functions often underperform, making focal loss a practical and reliable alternative. These real-world examples show that focal loss isn't just a theory. So, let's now take a look at how this plays out in practice. Now, let's dive into a hands-on example and see how focal loss actually performs compared to standard binary cross entropy. For this demonstration, I implemented both loss functions inside a simple neural network using PyTorch. The task was binary classification on a highly imbalanced fraud detection dataset, essentially a realistic setting where false negatives can be costly. To evaluate consistency and real-world behavior, I trained each model 5 separate times. Doing so allowed me to observe not just performance, but also the variance across runs, which is especially important when working with stochastic models and noisy data. So, let's take a look at what happened. Final takeaways. To evaluate each model's consistency and real-world usefulness, again, we trained both the binary cross-entropy model and the focal loss model across 5 independent runs. Doing so helps account for the randomness in weight initialization and data splits. So, what we observed was that focal loss consistently outperformed binary cross-entropy. Not only did it outperform, but it did so across all key metrics, especially when it came to precision and the F1 score, which are both crucial when identifying rare fraud cases. While binary cross-entropy had relatively high recall in some runs, it often came at the cost of precision, misclassifying far too many legitimate transactions as fraud. Focal loss, on the other hand, found more true frauds while keeping the model from overfitting to the dominant class. It showed some variability in precision, but overall, its ability to identify rare, high-value cases was much more aligned with the real-world goals of fraud detection. In practice, we'd rather capture more actual frauds, even if we accept a few false positives, especially when those positives could be flagged for manual review. Thanks again, everyone, for your time and your attention. To wrap things up, focal loss offers a clean, scalable solution to one of the most frustrating problems in machine learning, which is class imbalance. It shifts the model's focus toward the rare and important cases, which is exactly what we need in high-stakes domains such as fraud detection and healthcare. It's not just effective, it's also lightweight and very easy to implement, often requiring just a few extra lines of code. So, with that, I hope this presentation showed how a small tweak in the loss function leads to significant gains in model performance and reliability. Sometimes, one equation really can make the difference.